In this last test corrections video, I want to just show you the free response. You do not need to create your own for this section, but it is really important that you understand the free response problems and that you continue to practice the ones that you didn't have time to finish or that you didn't understand well enough. The first question was a related rates question, and you should have recognized that both because of the word rate in the problem and because fundamentally it's talking about things that are changing with respect to time. The work is very short. You can see it all on the screen. Organizing your work will really help you appreciate how quick it is. So I would have started over here. The question says, what is the rate, at what rate is the radius expanding, which means I'm looking for dr dt. And it says when the radius is 5 inches. 5 inches is when the radius is what the radius is at one moment. It's not always 5 inches, so you can't just plug 5 into the volume formula. But we do know that the rate of change of the volume is a certain number. So I take the volume of a sphere, which is a formula that's given, and I take the derivative of both sides with respect to time, which is just a simple chain rule right here. Multiply times 3, reduce the exponent, and the derivative of r is dr dt. After that, I can plug in the numbers, including dv dt and the radius, and I can solve for dr dt. Not so bad. Question 2 was a multi-part question. The first step would have been to just graph this function using your graphing calculator and the correct window. It looks like this, and then I've marked these points. It was really important that you use the exact values in order to get full credit on this question. And the points in question are the intercepts and then the 3 vertices. When B says where is the f increasing, you have to really remember that this is the derivative function. So we don't actually care where the derivative function is increasing. We remember that if the original function is increasing, then the derivative is positive. So the y values of this function are positive all through the middle of this graph, specifically when x is in between 0.282 and 3.759. This whole section of the graph, since the y values of the derivative are positive, f is increasing. Next, the question asks where f has local maxima. So remember what it means to be a maximum. It means that the derivative equals 0 and the derivative switches from increasing to decreasing. In other words, the derivative switches from positive to negative. That happens right here at this value. The derivative is positive, and then at 3.759 it turns to negative. At that value, the derivative is 0, making it a critical point, and going from positive to negative makes it a maximum. Inflection points are where the concavity changes. In other words, concavity changes when the derivative changes from increasing to decreasing, not from positive to negative, which is what we were just looking at here. Here, the derivative is increasing, and then it now switches to decreasing, which means that the derivative of the derivative, or the second derivative, is going to equal 0 at that point. That makes it an inflection point. At this point, the derivative goes from decreasing to increasing, which means the second derivative goes from negative to positive and equals 0 right there at 2.166. And again, right here, when the derivative function has a vertice, the second derivative will have a critical point, or a 0, which makes it an inflection point. So there were three inflection points. Okay? You got a point for each section's explanation and an extra point for knowing the exact values, which just means you knew how to use the calculator to find these numbers. The trick to sketching is to reinterpret each of these pieces of information in words. Many of you wrote them out here at the side, which is a great technique, but I strongly encourage you to try writing them out in your graph. It'll help your sketching. So when the instructions told me that f prime of -1 and +1 equals 0, I knew that there had to be critical points, or at least a horizontal tangent, at -1 and at +1, and I used those orange lines to indicate that. Next, it told me that when x was less than -1, so that means the left-hand edge of the graph, f prime is positive, in other words, the function's increasing, but f double prime is negative, which means it's concave down. So I wrote increasing and concave down. This whole section of the graph is increasing and concave down. Next, in between -1 and 0, which is this skinny little section of the graph right here, the function should be increasing and concave up, which I indicated in words right here. Between 0 and 1 on the x-axis, which is this section right here, the function should be increasing and concave down, which means it switches right here from concave up to concave down, making that an inflection point. And then, of course, the last section of the graph is decreasing and concave down, which looks like this. Then it's just a matter of connecting the dots. And, of course, the same shape could have been moved farther up or farther down, but that's the fundamental shape that you should have. The last question was really a beauty. The work is long, so I'm going to scroll through it. You would have wanted to start with the setup and then indicate somehow that the top costs $5 per foot squared and the bottom costs $1 per feet squared. Notice that I use the same variable s for the two base sides because the base is a square, and that was a really important detail that you needed to recognize. I also recognize that the total cost 72 has to be the cost of the bottom and sides and the top. Well, the bottom of this box is s squared, and the sides are all h times s, and there's 4 sides. So s squared plus 4 sides right here is the total amount of material that costs $1. So the cost times the amount of area. The top of the box is another s squared, but the top costs $5 per feet. So this s squared times 5 is the cost of that glass top. This expression can be simplified to this one, and we can solve for h, which we'll use in a second. I probably would have started the work before I realized that I wanted to isolate h. The work itself, this is an optimization problem. We want to optimize volume, so I need a function where volume is the output. The volume of a box is base times height times width. For my particular box, the base and the height are the same number, so I use the variable s to indicate that. Now, I know that to optimize this function, I need a function with one variable so I can take the derivative and find the extrema. So I'm going to replace h using the information about the cost because I can get an expression that has s in it. So I substitute in right here, and I really just simplified. I split it into 2 fractions and simplified, but either format could have worked fine for you. And then when I simplify that, I encourage you to always simplify as soon as you can so that your derivative is easier to take. This becomes my expression for volume. Once I have the expression, the rest is just easy calculus. Check your endpoints, check your critical points by setting this expression equal to 0 and solving for s. When I do that, I get +3 or -3, but remember s represents a side length, so -3 is not a useful answer in this context. And then I use the first derivative test to confirm that that really is a maximum and not accidentally a minimum. The answer that I'm looking for are the dimensions, so I take the side length 3 and I plug it back into the height formula to determine what the height should have been, and then into the volume formula, that one, to determine what the volume should have been. Not so hard.